Now on to something that seems a little mundane to most people, but actually there are some high energy particles causing some interesting things at Jupiter. And Patrick's here to tell us all about it.
Right, so let's go to Jupiter, our solar system's largest gaseous planet. There's been a 40-year-old mystery about what causes Jupiter's X-ray aurora, and that has just been solved. Here we see an image. The purple here represents the X-ray emissions from Jupiter's aurora as detected by the Chandra Space Telescope in 2007. And it's superimposed against the Hubble Space Telescope image that you see there in black and white. Now, these X-ray pulses were kind of detected every 27 minutes, kind of emanating from the poles of Jupiter. And scientists knew that these aurora had to be triggered by ions crashing into Jupiter's upper atmosphere at that polar region. But they didn't really know the mechanism of how those ions got there in the first place. What about these ions? Where do they come from? Well, there's a lot of ions being spewed out by the volcanoes of Io, and you can see all of that in the orange there. This is a major source of ions, mostly charged sulfur and oxygen atoms, kind of entrapped within Jupiter's intense magnetic field. So what did they do? Well, back in 2017, in an effort to solve the mystery, 2 spacecraft were used to make measurements of Jupiter's X-ray emissions over 26 hours. On the left there, you see the XMMNewton, which is used to detect the X-rays coming from Jupiter. That's run by the European Space Agency. And that right is NASA's Juno spacecraft, which is currently in orbit around Jupiter. And that was used to take readings from the magnetic fields inside of Jupiter. So what they found was that the pulsating X-ray auroras are caused by fluctuations in Jupiter's magnetic fields. And as the planet rotates, the magnetic field kind of gets dragged around by Jupiter's rapid rotation. Also, another factor is that when the magnetic field is compressed by the solar wind, these changes can be detected by Juno, and they were when Juno was getting close to a flyby of Jupiter, millions of miles away from the planet. There was a compression of solar wind against the magnetic field. This compression heats up the ions and triggers what is known as an electromagnetic ion synchrotron wave. And so that's a big word, but basically it's just an electromagnetic pulse. And just imagine the particles riding along like a tidal wave, but electromagnetic in that sense, along the magnetic field lines. So these ions actually moved. Initially, they kind of stay there trapped in Jupiter's magnetic field and they don't do anything. But now they're set in motion by a change in the magnetic field, and there's a force applied on these particles. So what happens? Well, the particles move along the magnetic field towards the polar regions. And here they are. And you get, should you get another solar wind compression, you get another surge of particles along the magnetic field lines. And in the red circle there, you can see that a bunch of particles are about to interact. And once it does, you get a burst of X-rays. And that pulse of X-rays generated from the South Pole there is detected by the XMMNewton spacecraft out in Earth's orbit just a few minutes later. That's the kind of mechanism that's happening there. Here we see a similar thing happening in the northern hemisphere, northern polar region. So Jupiter's aurora process is quite different from the Earth's, where, you know, normally when the sun is very active, we get a coronal mass injection, a bunch of charged particles interact with the Earth's magnetic field, they go down the field lines and then towards the poles, and then collide with the Earth's upper atmosphere, where we get these brilliant northern and southern lights that we normally see, and the invisible light. But at Jupiter, it's the ions from the moons of Jupiter, mostly Io and some other moons, where the within the magnetic field that crash into Jupiter's atmosphere and trigger compression, which is triggered by compression of the magnetic field by the solar wind. So that's a very different mechanism. It's something that scientists are excited about because This could happen, say, on other gas giant planets like Saturn, with its moon Enceladus that has ions of hydrogen coming off from the water. So very interesting mechanism, and done in collaboration with two spacecraft, which confirm how this happened. Another discovery is a brand new moon of Jupiter has been discovered by an amateur astronomer by the name of Kai Li. And if it becomes official, the total moon count goes from 79 to 80 moons of Jupiter. Now, this moon orbits in a region where we see the orange, red orbit lines there. It was discovered in infrared images taken in 2003 by the Canada-France-Hawaii telescope. That's the data was actually available to the public on the web. And this moon is believed to be a member of the Kami group that orbits in the opposite direction or retrograde to Jupiter's rotation. The moon in this region, the moon Carney, is the largest one in that group, and it's about 46 kilometers in diameter. Now, as we look at this diagram, look, all those orbits look very close, and that's because this diagram is not to scale. The orbits of those of the Carney group in this orange, all those orange lines there, are actually not to scale, and even the banana is not to scale, but they're actually about 22 million kilometers from Jupiter. And so that would be way out of this image there. But we've kind of thrown everything together to give you a sense of the direction of orbit. So how are these moons discovered? Well, the moon Carney was discovered by the WISE spacecraft in 2014. And it took a series of images, basically. I'm going to run this again here, go back. And you can see these individual images. You just barely see the moon. But what they did was they put all those images together and combined them. So you can see all the images stacked and to visibly show the actual moon in the center here. So in a similar fashion, the amateur astronomer went on the web, looked at the data from the Canadian-France-Hawaii telescope, and found a little smudge there. You can see it, it's within the ellipse, and there's a little arrow there and pointing to a smudge. And I'm just going to step through just 3 images here. This is the first one. And the next one, you can see the smudge has moved and the background stars has. So exciting discovery there. All right, so talking about discoveries, Jupiter is being orbited by the Juno spacecraft, which continues to reveal some of the secrets of Jupiter. The Juno spacecraft made its 35th close pass of Jupiter. It's called, the close pass is called Perijove, and it's Perijove 35, and it gets as close as 2,600 miles, but this time it got even closer, a mere 2,000 miles above the cloud tops of Jupiter on the 21st. Also, something interesting here, you saw that beautiful flyby of Ganymede and Jupiter at the beginning of this program. That flyby of Jupiter changed the orbit of Juno. It had a 53-day-old orbit around Jupiter, and now it is changed to 43 days. So I'll be reporting 10 days sooner than for the next Perijove. So what do we see from this Perijove? Well, again, Juno continues to really excite us and the public and the scientists with these incredible, beautiful pictures. Here we see the northern polar region, a region that you can't see from Earth because it's kind of hidden. This is centered on latitude 75 degrees, and the North Polar region is at the bottom there, right there with the laser pointer. Right there, that's the pole of Jupiter. Now, this picture was taken at, this is one of the closest pictures taken of Jupiter's cloud tops, 2,052 miles, where you can see incredible detail. Just bear in mind, this isn't the entire disk of Jupiter. This is a fisheye view. So where you see the edges there, that's the edge of the camera, the horizon that the camera can see from that vantage point. A little bit further away, about 400 miles higher than the previous picture. Incredible detail, intricate details of these swirling clouds of Jupiter. And those white cumulus-like clouds are actually ammonia ice crystals that pop up kind of thunderstorm clouds. And again, beautiful swirly brown spots and also other storms visible here. And you get a sense, looking at these images, you can actually see some of the shaded kind of relief of these clouds just by looking at the shadows of those cumulus clouds. You can actually almost see a three-dimensionality of these images. And our last picture, this is one of many that were processed by the public, is a view of what on the left Jupiter would look like to our eyes if you were in the vantage point of Juno. Kind of not quite bland, but there is some detail there. And then on the right, a color enhanced image to show this exquisite detail of fluid dynamics happening in Jupiter's atmosphere. And that's it for the Jupiter report.
Well, thank you, Patrick. Always interesting to see these beautiful images coming from Jupiter, and the work that people do on it to bring out these details can be done by all of you out there as well. Patrick has created tutorials on these that you can find on our webpage that tells you about how to download the images, how to convert them, how to load them, sharpen them, color them. Go have fun. It's part of what these missions are all about, engaging the public with the astronomy, and it's brilliant. It's a good time, and we've told you how to do it. Now, what's also a really great time, well, some of the questions we've been getting are great. I want to answer one very quickly. Someone wanted to know, what could we be finding out about Jupiter that could be applied to exoplanets out there? Well, we have a lot of Jovian-sized exoplanets and larger. And Juno has been studying the internal makeup of Jupiter. We've learned some details about it, and we've also learned about sort of the conveyor belts of energy that are going on between Jupiter, its ionosphere, the auroras Patrick was just talking about. Someday we will have telescopes that will be able to see if those are happening on other exoplanets and pick these things up. So pretty much everything Juno is learning about Jupiter can be applied to Jovian-sized exoplanets. It's a really exciting time.